So my name is Matt Farrow, and welcome to the Aspirants Podcast. This is our first episode, and today I'm going to be interviewing Dylan Brophy. Dylan's one of my longtime friends. We met in middle school, actually, and we've been close friends ever since. Did some programs, learned a lot about trading together.
All sorts of random
projects. But I brought Dylan here today to talk specifically about artificial intelligence. Dylan's been programming for the better part of the last decade. So we'll go ahead and kick things off. Dylan, what is AI?
Okay, so in order to understand AI, you have to understand, first off, that it's sort of different than traditional programming. So traditionally, what a programmer does is feeds a large amount of instructions to a computer on how to do tasks. It's sort of like your teacher, telling you how to do an equation or something, right? So it's much more complicated, for a video game, you get millions of lines of code, but those are instructions on what the computer should be doing. The difference is that AI does not really work like that. Instead, it learns what the instructions should be based on some other form of information that's not instructions. And so that's really the best way I think I can describe it. And the reason that you would do that is the programmer doesn't have to know what the instructions are and doesn't have to think through it. Something like catching a ball is very easy for a human, but it's very hard for us to describe how to do it because it comes so naturally to us. It's something that's embedded in our brain's framework, and so it's much easier to basically lead the computer by example than it is to give concrete instructions in some cases.
Right. That's interesting. And so I think that's a very good definition of AI, right? AI is having a computer solve a problem on its own,
yes.
Right? So to speak. So can you give us an example? So what does that actually look like?
So do you mean from an algorithmic perspective, or do you mean from like a real world use case perspective?
So maybe we could talk about a few of the different architectures for artificial intelligence for an AI program. And then also the second part to that is how do these architectures work?
Okay, so there's many different types. A few common ones, you have your neural networks, which are very popular right now, which is why I mentioned them first. And if you're doing machine learning stuff, that's probably one of the first things you're going to learn, if not the first. And that's important in natural language processing, image recognition, these sorts of things. Another one is what's called genetic algorithms, which is basically just applying Darwinism to computer programs.
That's a good way to put it.
Yeah. So basically, you delete the versions of the algorithm that don't work well and create more variations of the programs that do better than the previous iteration. And repeat that often enough, you'll end up with a good program. Let's see, what else? Another one I've heard of, I haven't seen this actually implemented, but I'm not sure if it should be classified as a machine learning algorithm, but I think it's worth mentioning is simulated annealing, which originally came from the idea of how you anneal physical materials and such, and applying that to programs. People just quit calling me all the time sometimes.
Yeah. You should learn how to silence your phone. Come on. You know all about AI, but you can't silence your phone. Okay, so.
All right.
So annealing.
Yeah, so basically that's particles in the physical world want to reach a lower energy state, right? This is entropy working out. And so it's just trying to become more stable over time, but since you're programming it, you define more stable as more successful. But there's some randomness in it that allows you to find more variations of the algorithm, if that makes sense.
I think so, yeah.
Okay, yeah, it's kind of a weird concept, but yeah. So those are kind of three that I've seen and heard about. As far as how they work, neural networks, kind of obvious, it's just neurons, right? but it's important to understand they're very different from the human brain.
Right.
Because the human brain is ridiculously complicated. You have more neurotransmitters than we're aware of, probably by a magnitude, at least, maybe 2 magnitudes. So we could have, 100 times the number of neurotransmitters than what we even know exist. And that alone adds a dimension to biological neurons that computers don't have. Because for a computer, it's just the activation signals in and out, right? It's like one number. Next thing is that the brain has neurons connecting in all sorts of different directions, and also, just the sheer number of connections.
Right.
And so we're kind of starting to replicate some of that stuff in the computer, and that's really interesting. But I think it's important to understand that we're not so much talking about real physical neurons so much as we're talking about very large matrices in linear algebra. Okay. With the machine learning. Does it make sense?
Yeah, I think so. I have a couple of questions.
Okay.
So one of them is, we have this idea of evolutionary algorithms. And so basically this is a way of applying like the dynamics of emergence, per se, to finding a solution. So it's like we create all possible sub-solutions. I want to understand if I am conceptualizing this correctly. It's like at the base layer, we have some assumptions. And then off those assumptions, we generate like a bunch of different possibilities of answers. And then every successive generation, we go ahead and we take the best answer that we've seen and we mutate it. And we repeat that process over and over again until we get a solution that meets our criteria. Is that how that works?
More or less, yeah. Yep. So, and honestly, I haven't had much success with those.
Okay.
But in theory, it should work, and I believe that, if you look, you can find practice of it working well in the real world. But, yeah, essentially that. It can be weird to do the mutations, though, because if you're essentially trying to generate an algorithm, you're trying to automatically generate code, and so it's not like you're taking like a few numbers and just increasing them and decreasing them randomly.
Right.
Right, which is closer to what a neural network is, although it's not as random. It's like you're trying to make these structures different shapes and then change the numbers inside those structures and create new numbers and remove ones and like all this craziness in some cases. And so it can be quite complicated, but also very interesting to see what the computer does.
Right. And so maybe on one side we have evolutionary algorithms, which are a form of AI. And then on the other side, we have neural networks. And so, like, kind of what you were just explaining, I want to kind of reiterate this, but it's like neural networks, they define a solution space that is smaller than evolutionary algorithms, because in evolutionary algorithms, you have some structure and you're changing not only the parameters of that structure, but also like the structure itself.
The structure, yes, you can. And to be fair, you don't have to. But hypothetically, yes. But I think in practice, neural networks are so large. You're talking about, for image recognition, millions of parameters. And I wouldn't think that you would do that with a genetic algorithm for various reasons.
Right, and so this kind of brings me to my next point, which is, all right, so these have unique characteristics. And so what are the different applications for these two sort of ways of generating artificial intelligence? So what are specific applications where it's like, I think applying evolutionary algorithms would be a good thing to do in this instance. And I think that applying a neural network to create an artificially intelligent system to solve this problem is a good use in this instance. It's sort of like the variability or the amount of things you know, the amount of information you have. Like if we just take the image software we were talking about, it's like, okay, well, an image has very defined parameters. They don't change too much. Yeah. But maybe if we wanted to say like find like a system that has a lot more randomness, um, like say the stock market, maybe it'd be better to use evolutionary algorithms in that point, or no, or where do you draw the line? How do you determine this is an evolutionary algorithms problem? This is a I think neural networks is the way to solve this problem. How do you determine that?
Okay, so you first have to understand the limitations of them. One is that genetic algorithms are, in my experience, slow to converge. And convergence is essentially how fast, speed of convergence is it's like the speed of understanding something. It's how fast it can get to the solution, a good solution, right? Um, I would say I've found that neural networks seem to be faster than genetic algorithms. If if the genetic algorithm finds the answer at all, okay. But neural networks do have some limitations. So the inputs for a neural network typically are bounded between a certain range, right? So this could be like -1 to 1 or 0 to 1 are typical. So for an image, your red channel is 0 to 1, right? Red 1 is full brightness, 0 is black, right? In each channel. Or it could be grayscale, right? Same thing. Whereas for something like the stock market, how do you translate price data into that? And that's a question where you have to ask that. And some other problems, I don't remember what exactly I was working on, but you can't take all numerical values or all sorts of data about structures and convert it into this sort of finite space where it's all between say 0 and 1 or -1 and 1, especially since neural networks typically have a fixed size. So that means your number of inputs is fixed. And so that limits kind of how complex and the range of complexity your data can have.
Interesting.
Right? But in reality, neural networks become so much larger that they can take things that are really complicated, like an image, and analyze it. Whereas I highly doubt a genetic algorithm could do that.
And so, can you combine the two?
Yes. And this has been done. There's actually a great demo online where I don't remember what it's called. I think it's quite popular, but it generates like these. You're able to like make these life forms by drawing boxes and like connecting them, and they're like wiggly things. Yeah. And it sort of generates and trains these neural networks by evolution. So yes, you can combine them, and this is like the case where the neural network can change size and get bigger over time. But yeah,
interesting. Okay.
And it's funny because it quite often finds solutions that you would have never expected. And it's just like, why is it doing this? Like, why is it like leaping around in this weird way, but it like actually works really well and like every time.
Yeah. And
it's just so that actually reminds me of that case where genetic algorithms do work quite well in that demo. But it's like creature creator online or something. It's like it's
all right.
You should check it out. It's funny. It's fun.
Yeah, I'll have to look into that. So this kind of comes back to like when you're creating artificial intelligence, right, it is a form of intelligence, and you use intelligence to solve problems, right? And like maybe you use intelligence to understand the world, right? Because maybe that's a problem that you have to solve. Is like I want to understand the world. So I guess there's different ways that we think. Like there's different intelligences, like, or if there's one kind of intelligence, that there's multiple ways that people can achieve that intelligence. There's different thought architectures. There's different metacognitive models. And so for me, we've talked about this before, but I'm a predominantly categorical thinker. And so I like to compare things to each other. And so I think you are more of, if we could call this a vertical thinker, where it's like you tend to go in depth and you tend to be more systematic and careful with your thoughts. If we compare those two kind of models of thinking, right, on one hand we have the evolutionary algorithms, and on the other hand we have neural networks. So which one would be the sort of categorical thinker, like maybe the creative person? And which one would be the sort of engineer, the architect, I'm thinking within depth. I'm controlling my thoughts, and I'm binding them in a very limited space so that I can go down, as opposed to sort of considering all possible things.
Right. I would say that, I mean, if we were going to phrase it that way, I would say that.
And these are limited, right? There's many different ways to think. These are just two ways that I thought of right now.
The genetic algorithm is probably more sort of categorical, but I also hesitate to compare that because it's not thinking the way that humans do, where you're comparing all this information. It's not doing that, which, whereas neural networks are doing a type of processing that every human does, but none of us are aware of consciously.
Right. It's sort of the mathematics that are involved in movement. Like you're actually doing a ton of math when you walk down the street, but it's like, and that's like ridiculously complicated. And it's like we do all this subconsciously through intuitions. And so these intuitions are neural networks, right?
Yes.
Yeah. Okay.
And also specifically for the vision. And the reason I mention vision is because it's so complicated. The human eye is remarkable. Okay. And I could go on and on about it, but basically it's better than the eyes in almost any animal ever. And that would make it sound like the eyes are expensive, but actually the expense from the eyes is in the brain, because the higher the resolution of the image, the more work the brain has to do to analyze that image. And so we have much bigger neural networks for image processing than other animals because of that. And it's huge. It's depth. They're very large, deep neural networks, very well connected. And it's the difference between that and the way that we would normally think, or the way a computer thinks, is that it's all parallel. It's all happening at once. It's like it's like thousands of channels.
Right. I think that makes that's a lot of sense, right?
Yeah.
And so, in some sense, like computers are linear.
Yes.
Generally, right? And so this is one explanation for, like, if we're solving problems in a linear fashion, right, we're going to be confined by like we're going to run into our constraints first, as opposed to like if we solved problems like horizontally. Because the way I'm just thinking about this right now is like, okay, there's some problems that are the linear solution is just the fastest. It doesn't make sense to compute it in parallel. Or it's like maybe there's other problems where it's like, okay, it actually makes sense to solve this in parallel.
But the type of parallelism matters, and this is kind of branching into another topic, but there's a big difference between running a program on 8 cores and running a program in the hardware equivalent of that.
Right. It's like a dynamic parallelism, where it's like you need to be able to expand or contract how many.
No, you don't want to. No, because then you have to do more work on the hardware. It's slower.
Really?
Yep, it's way slower. Because when you have multiple cores, you're still thinking linearly, just at multiple points at a time, and then you have to coordinate all that. It's a mess. It's horrible, and it's slow. Okay, the best type of parallelism happens to be the type of parallelism in neural networks where you have essentially you've taken the problem and you've completely separated it into many, many problems.
Right.
Okay. One neuron is only focusing on its inputs and its outputs. It's not having to worry about anything that the rest of the system is doing. The same thing with transistors. The same thing with a GPU, right? The GPU has all these nodes that each one is processing one, triangle at a time, or one point on one triangle at a time. It's one problem, right? And it takes it all the way through to the end, right? And that's a lot better than having multiple cores, for example. So that's kind of where it shines. But there's other problems like finding prime numbers that you kind of can parallelize, but it's also a lot harder.
Right.
Right. It's like, how are you going to divide up the work? And then there's overhead to divide up the work. Right. It's like running a company. You have to figure out how you're going to manage all these people.
So there's
many
overhead costs, right?
Yes, and those can be really bad. And if you make a mistake in doing that, which is very easy to do because you're not adaptive, because your head's not in the computer, it's all going to get screwed up. And there's all sorts of stories of that happening. Okay. So anyway, that's kind of why that's important. I think, and like for the vertical thinking, there's I have not really seen a machine learning algorithm that actually does that.
Hmm.
I mean, you can do it with neural networks, but I would argue that it's kind of nonsensical, because it's, again, you have to deal with the finite space, and there's all sorts of tricks you can do with the neural networks. I mean, you can feed them back into each other. You can, now there's like, I think MIT came out with these liquid neural networks, which are really fascinating, by the way. And that's a whole other topic again, but they're even more like the human brain, right? It just keeps going there.
Right.
But it's still, the neural network does not think like a conventional processor.
Okay.
So you have to do extra work to implement it on that.
This is actually kind of my next question.
Okay.
So our current hardware sort of like my computer, right, that I have in front of me. Is this architecture set up in a way that really gets the most out of neural networks? Or is my architecture optimized for a different kind of computing?
Well, to some extent, it depends on when you bought this Apple laptop of yours due to the M1 processor.
Okay.
But just the general case is...
It's old.
Not really. Well, the general case with computers right now is they're set to think differently than neural networks.
Okay.
Even GPUs are designed basically to do heavy linear algebra, which, again, that's basically what neural networks are, but it's not really put into the hardware as much as it could be. And there's companies that are working on that, and that's going to be coming, the next 5 to 10 years. You're going to have chips that all they do is neural networks.
Interesting.
That's it.
And so how does the architecture change? How do you favor or facilitate sort of like this computation and how do you optimize for this?
I don't know exactly how those companies are making the chips, but I would imagine that you essentially have all these different stages on the chip that more or less are structured like a massive neural network, and you could probably cut it into pieces, right? And so you're putting in things, you're doing some floating point calculations, which basically is like just numbers with decimals. You're doing a bunch of math. And then you pass it to the next speed, which does a bunch of math, right? And that's how I'd imagine it works, is something like that, or something like GPU. But the key difference is that you're dealing with less precise numbers, because neural networks deal with errors really well. So if your number is off by 1%, which is big, it doesn't care. If the values of the graphics are off by 1% in a video game, you're going to notice. With a neural network, you won't.
Right.
So you can deal with smaller numbers, and those are faster to compute, and they're less complicated. Okay? So that makes the hardware faster. Then you can configure the connectivity so that you're routing all your signals to where they need to go in a fast way. Because in order to get your data where you want, you have to make sacrifices, right? So you have to keep in mind what your thing is going to do, what your device is going to do. And if you know that it's going to be a neural network, and that's all it's going to compute, you can make the routing of the circuits efficient for that particularly. Does that make sense?
Right.
I don't know how far they take it. I don't know if they're doing training in hardware. That would be really cool. But you could really take it really far.
Okay.
But your processor, as we've had them since forever, a Turing machine, is not set up to run a neural network. It's designed for a different class of problem that is more dynamic and more complicated and more changing, sort of like a genetic algorithm where you're dealing with different structures of different sizes, and they're changing shape and size, and you're modifying numbers, and you're dealing with all these different types. It's general computing.
Right.
Okay.
Which is different than...
Different.
Right.
Right.
And so this kind of brings me to the next point, which is we have AI today, and AI has a bunch of different use cases. And so I've always kind of conceptualized AI on sort of like as like sort of a function, like the intelligence of AI systems. And right, people say it's exponential. And so maybe you could kind of talk about this, like say it's an exponential function, like first of all, like what does that mean? But then also, what are some of the points on that function? Like, where are we today, right? And then where will we be in like 10 years from now? And then also, how will, I know this is a lot maybe, but also as we change our hardware, how is that going to change AI as well?
Right, like the chips I was talking about?
Yeah, like to what extent are we bounded or limited by the AI algorithms we have today? And to what extent are we limited by the hardware that we have today? And how's that going to change?
Okay, so the first thing with the growth, I think that it's exponential to a point. And the reason is it doesn't make sense for an exponential curve to continue forever in the physical world. And there's a lot of reasons for that, but it basically comes down to physical resources and energy and how much computing can be done in what amount of space and how much that can actually benefit. I do believe that there's an infinite amount of things to learn. Actually, I could probably mathematically prove that if I really tried. That's how much I believe it. However, most of that stuff's not useful.
An infinite amount of things to learn.
Yes, you could learn every single prime number. There's an infinite number of prime numbers. Right.
Okay, yeah.
There's probably way more complicated examples of that, many of which are probably more useful. However,
with respect to intelligence.
Okay, yeah, but the benefit of whatever you're learning, at some point is going to diminish within a finite space. So it's like what needs to be learned is going to change. Okay, so if we're talking hundreds of years, maybe even thousands of years in the future, and AI has a serious presence in the universe, at some point it's going to start depleting its energy sources. We as a society, are going to need to find more energy sources and these types of things. We're going to be bound by the amount of material we can mine and how fast we can move it around, right? And so at that point, your learning rate will decrease because your learning rate is, your learning and your learning rate is kind of what drives the improvement of the system overall, okay? But it's a feedback loop because as the system improves, it makes it easier to learn, right? But eventually quantum computers will proliferate. And then the question is, will there be something past that? Will be like a second quantum computer, right? So anyway, there's a lot of reasons and a lot of ways that the curve could kind of level out. And I just don't think it makes sense from a physical perspective for it to just go exponential to infinitum, right? However, I could be wrong. I mean, I could be wrong about that. And it's really hard to predict because we don't know how that's going to go. But anyway, we're keeping that in mind. What's kind of the next stages? I think that it is absolutely possible for us to have general intelligence. And for those that don't know, that's a computer as intelligent as a human. I think that's possible in the next 10 years. And I think that unless humanity gets wiped out, it will definitely exist in the next 100 years. I would guess that it'll probably exist. If I were to guess as to probably when it'll most likely exist, sometime in the next 20 years. I would think.
And so...
And, that's assuming there's not another AI winter, but anyway.
What do you think of the idea of the singularity? That single point when AI becomes smart enough to change itself, to make itself smarter?
It'll happen. And it'll probably happen not a super long time after general intelligence. Matter of fact, even an AI not as smart as a human, we're talking, let's just say you gave the computer an IQ test, it tested lower than 100, okay, so below average. That doesn't necessarily mean it can't improve itself.
Right.
Okay. So, you could see it just start to improve itself constantly. And
there's this idea of effort too, where it's like, it's not confined by, the same limitations that we are. Like, computer doesn't get burnt out, but we get burnt out, we get tired.
It can also just get a bigger computer. It can run in parallel. But as we discussed, there's limitations to that, right? So you get to a point of diminishing returns, just like in the stock market, how, you make less profit the more money you put in by percentage, even though it's more profit in total, right? So is the same with upgrading these things, because it's like, okay, so now your server room is literally the size of Texas, but it takes, 10 milliseconds of the data to get from one side to the other, and then you have to transfer all this stuff, and where's the memory stored? It becomes a mess, even at that scale, right? So how much does it really help you? Because each time you scale, it's going to help you less.
Right.
So I think that's, like I said, I think there's some sort of plateau, and maybe it ramps up again. Maybe there's a second exponential hit. You can have that, but it won't, but in any case, I think that soon after, and when I say soon after, I mean like probably within a decade after general intelligence happens, we're going to see it being dramatically more intelligent than humans by magnitudes.
And so what does that mean?
That's a sticky question.
Right. There's all these different kind of ways to conceptualize higher beings, or higher forms of intelligence. It's like they might look at us like ants. And oh, sorry, I stepped on an ant. I didn't mean to, but it was in the way, or I didn't notice it. And in some sense, we might think that an advanced civilization would think the same thing about us today. And so, what are the concerns with this? Are they warranted?
I think a lot of the concerns are warranted that have been peddled. I'm just going to briefly go over them. They've been discussed to these topics of concerns about AI have largely been beat to death in other areas. So I'm going to try to hit on areas that haven't been talked about as much. Okay, but briefly, we'll just go over the common concerns of, a sort of AI apocalypse where an AI takes over and there's something that goes wrong in its programming, or it was programmed to be malevolent, or whatever it is, and it either, it somehow ruins humanity either via extinction or making life just miserable. That's something that can happen, and we have to be careful about that. But it's been discussed to death in other places, so I'm not going to go further than that. The next is a war between AIs. Suppose that you had two programs. Doesn't matter if they're benevolent or malevolent, the fallout of a war between them could be catastrophic for humans. Okay. So, that's another thing. But there's other concerns. One is, I more so want to talk about jobs and the psychological effects on us. I want to talk about that. And I think that hasn't really been discussed. First off, humans will not be very useful if we do not improve at that point. There will be nothing that the computer cannot do that we can do that it cannot.
Right.
Okay. There will be things that we do that will still be appreciated, that we'll want. I don't think it'll take away from artwork really so much, but there'll definitely be a heavy AI presence in art. And we're already starting to see that, but it's going to be very prevalent at some point.
Right. And it's like, there's kind of this cool question where it's like, okay, art tells us something about the human experience. And so for an AI to create art that we didn't create, it's like, maybe it can tell us something about the human experience that we weren't aware of.
Or perhaps something about the machine experience.
Right. That's a really cool way to think about it too. Right. So what's
the difference between the two? It's in a way a descendant of man, right? But it's also not man at all.
Right.
It's completely different. And so, what is it? It's an expression of both. It's an expression of what man created, but it's also an expression of from the thing that man created, and what it's like to be that, and what that is.
There's a lot to consider there.
So I want to go more into like the AI job stuff.
Automation in the economy.
Yes.
Right. Because
so, like I said, artists that's still going to be valuable, and there's going to be the nice coffee shop that you pay extra at because there's humans there and they have more personality. But even then, that can be replaced. Okay, machines will be able to replace that. All of it. Mm-hmm. Every emotional response, every bit of it could be replicated. And So at some point, there's nothing left for humans to do. And I'm going to, just for the sake of argument, make the assumption that humans are not discarded and that we still run society at that point.
Right.
Okay, which that's a whole other topic that I do want to get into, but not yet. Even then, since humans have nothing productive to do that can't be done better than a computer, I think that it'll be a psychological issue that it's like, well, what's the value? Why am I here? And then you have also the opening of the possibility of an ultra decadent society where humans are not constrained by the physical world as much because every mistake that a human makes will be corrected by a computer. So to what extent can we make mistakes? Because typically when societies get decadent, they fall. What if it doesn't fall? What if we just keep getting more and more decadent? What does that lead to, and what kind of madness?
Right. I'm kind of thinking of, Wall-E.
Yeah.
That's what I'm thinking of.
Yeah, I think it would be like that, but significantly
Worse.
More extreme.
Right. And
like,
so,
there would not be a trash problem, for example. The computer would have solved it.
right.
Completely. End of story.
It's like sterilization in some sense. It's like, right, we learn, and a lot of meaning can be generated from suffering. And not all suffering is intrinsically meaningful, but a lot of meaning can come from suffering, right? And it's because, I don't know if it's because you need to suffer to have meaning, but it's because, like, meaning is sort of going towards your goals. It's sort of like going towards what you value.
Why go towards a goal when you can
Because
just
you
tell
have
a
to
machine?
move. That's the meaning of life. We were meant to move, right? And so we were meant to pursue things, whether that's psychologically or physically. And so, yeah, that's an interesting point. And I kind of wanted to touch on just this one other topic about automation and the economy. So we have like an economy essentially that becomes automated. We have people, no more use for people. And so I think we see something similar today where we have like a knowledge economy, so to speak. And it's like the knowledge economy is a lot of communicating with other people. And so there's two levels to this. One level is like, we've sort of automated a lot of the production from natural resources. So we can get large amounts of food very efficiently. It's not hard for one person to farm a lot of land and to be really efficient at it because we have really good tools for farming. And so there happens to be a lot of demand for knowledge right now, right? Content. But in some way, it's like you're paying other humans for something. And it's like you're paying the human for something just the human generated. But another part of it is like, okay, you're paying a human to communicate with other humans. And how valuable is that really? And so on one hand, you could say that's not valuable at all because you're not actually increasing the resource efficiency of the economy. You're not producing new things. But on the other hand, it's like, well, maybe thoughts are the things we're supposed to produce. Maybe that's what we're best at. And so I don't really know how to tackle this, but it's just something that I kind of thought of. Maybe this reliance on, maybe there'll be another kind of capacity that we can rely on other humans for, and that could serve as a transactional medium. Even if the resource and knowledge economy falls, maybe there'll be a third economy. What do you think of that point?
That's interesting, and that's possible.
Like maybe there's something about the human experience.
We'll only know when we get there.
Right? Maybe there's something about the human experience that's not intellectual, that's still valuable. And maybe if you have an artificial intelligence, sure, maybe you could learn these things, but maybe it's not optimized to, right? If you imagine like a whole subset of like optimizations that machine could have, a whole subset of specializations, like one specialization could just be to be a human, to be a human. That's a weird thought, but like maybe you have other subsets where it's trying to solve math problems, or maybe it's trying to create art, or maybe it's trying to, solve other problems. And it's like you need a particular individual for that thing. You need a particular set of thoughts, and maybe you have lower emotion in some of them than others. And there's this idea, I actually don't know who I remember hearing it from, but it was an idea of the neuro tribe. And it's like you have a bunch of different types of brains per tribe because we're so, in some sense randomly. I think this is the idea. You're sort of randomly given some sort of ability, perhaps in a tribe where you have a particular way of thinking about things that's useful, and you're specialized for that. So maybe you're a vertical thinker and I'm a categorical thinker. Maybe I can understand lots of different kinds of berries, but you're really good at making tools. And so maybe we work together, and that's like the idea of specialization. And so maybe you will have many different kinds of like instantiations of AI to do individual things. I mean, that's kind of an obvious extrapolation, but just something I was thinking about.
Well, it's worth mentioning because a lot of people won't think of that, but yeah, you're right. And it's hard to do everything well. To make specialized hardware to do every type of algorithm, it's difficult,
Right.
you know? And so you can't specialize all the hardware. So some of it has to be generalized, but that means it's slower. You know, so yeah, I mean, that's makes sense. I do think that as a species we should try to improve in whatever ways we can. And it could be something as simple as, you know, trying to be a better person or a better human, or, you know, seeing how advanced you can make yourself and how sophisticated you can make yourself. But it could also be, you know, something as complicated and lofty of goal as genetic engineering, you know. But I think that we should try to strengthen ourselves for the future.
How do you think we do that?
Well, I mean, using those ways that I described, you know, seeing how we can make ourselves more. And I think that because at some point, the thing is that living systems exist because they optimize resources and proliferation. This is natural selection, right? And if you have artificial intelligence and large amounts of artificial intelligence, at some point, the ones that rely the least on humans, if they really are doing a lot better than humans, you know, they're going to perform better, right? And they're going to exist more. They're going to be cheaper, cheaper, cheaper. And so eventually, and by cheap, I don't just mean humans paying for them. I also mean in the sense that they'll have to pay less for their own existence, in a sense, right? How intelligent they are doesn't matter. Whether they're sentient or not doesn't matter. But a system or pattern which is able to proliferate better will exist better. And
I think it's context dependent, right?
What do you mean?
Well, there's different environments.
No, there's not. There's one universe.
But there's different places in the universe that you can inhabit. And there's different things that you can pursue. There's different goals. Like an AI could have a goal to spread all over the Milky Way galaxy. Another AI might have a goal to just solve this one really complicated problem. And so it like would optimize for that. And so maybe like you have some AIs that are emergent by nature, but then you have other AIs which are definite. And so it's like they're pursuing different, if we want to talk about it like this, you know, like Jordan Peterson talks about like the emergent truth, but like there's also sort of a definite truth. And maybe you have an AI that just wants to propagate, you know. And what do you think about that? Is that?
I'm not. You're right, but I'm not. It's like I'm talking about power here.
Okay.
The most powerful being typically in our universe is going to be the one that is able to have the most income, so incoming resources, compared to the amount that is being spent. And that's a subtraction operation, not division. And that's important because that means that large systems are the most powerful because they can move the most materials, right? The most energy.
Conceptualizing power really is energy, like in the true physics definition.
It's energy.
Right.
Right. And that's what it's about. And that's also why oil is so important. Uranium and all this green energy, all this, that's why it's important. But in the same sense, power is power is derived from energy. If you can have the biggest body ever, but if there's no sugar in your blood for your cells to produce ATP, you can't move that body.
Right.
It doesn't matter, right? So the concern I have is the power would naturally shift to the most efficient and most robust system. And if that becomes AI, that will be powerful by default. And that's the other side of the conversation that I was kind of ignoring earlier just for the sake of argument.
Right.
And that's something that I'm thinking about and a concern that I have. And I'd also like to say, like, I'm excited about AI. I'm not trying to be a doomer here. Okay. I'm just saying these are things that we need to think about as a species and that we need to prepare for and find solutions for before they become an actual problem. Right. There's a window here. And we should be excited about all the things that we can learn from doing this and from this technology.
Right.
Right. So I'm excited for it and I'm pro AI, but we need to do it right. And there's a lot of dimensions of doing it right beyond just the conventional AI apocalypse story.
Right.
Okay. And that's what I'm trying to get at here. Does this make sense?
Yeah. I think that was a good conversation. I think we hit on maybe not all the particular components that I wanted to hit on, but I think we got a few, and that was good. So thank you for coming on, Dylan.
Of course. My pleasure.